students, and welcome back to study room. So as I told you in the last video, we're going to do the force experienced due to magnetism. Now you might think, how do we know that there is a force related to magnetism? Well, we know that because we saw that when we keep a magnetic material near a magnet, you see that the magnet pulls the magnetic material towards it, right? Like if you keep like so, when we can see that this stapler pin or any magnetic material is being pulled by the magnet, then we obviously know there is some kind of force involved, right? To pull or to push anything, you need a force. You all have studied about that in class 9th. So that is how we know that there is some kind of force that is involved in magnetism, or a magnet exerts some kind of force. Not just a magnetic field. Yes, it exerts a magnetic field in the area around it. There are magnetic field lines, but we know now that there is a force related to it too. So that is what we're going to study about. Okay, let's go. Okay, so current carrying conductor experiences a force. So this is an activity in your NCERT. Okay, so this is your activity 13.7 in your NCERT. So if you read up the setup of this activity, you will see that this AB is a aluminium rod around 5 centimeters in length. Okay, and what we have done is this magnet, this U-shaped magnet is actually called a horseshoe magnet. Why is it called a horseshoe magnet? If you've ever seen under the hooves of a horse, you'll see that there is this something shaped like this that is attached under the shoe of the horse. So the magnet is actually the same shape as the horseshoe, right? It's almost like the shoe of the horse, right? So that's why we call it a horseshoe magnet. So right now, you don't need to know, how is the pattern of magnetic field due to a horseshoe magnet. You just need to remember the basic concept that we studied in the bar magnet also. What did we study? That outside a bar magnet, what is the direction of magnetic field? It is from north to south. Outside, right? But inside, it's from south to north. So right now, we just need to remember, okay, outside the magnet is north to south. So if this is my horseshoe magnet, what direction would my magnetic field be in? Would it be in this direction or this? It would be in this direction, right? Because it is going from north to south. So this will be the direction of my magnetic field in case of a horseshoe magnet. Okay, so now you know what a horseshoe magnet is. So what we have done is, in this setup, we have taken this rod AB. We have vertically suspended it from this stand. You can see this stand. This is a stand. And we have suspended this wire in a way. Look at this. These two wires, they are basically holding, it's almost like this. Like this is the stand. And we have suspended this rod AB like this. But instead of suspending it just like that, we have suspended it in a way that it lies between those two poles of the horseshoe magnet. Okay, this much should be clear to you from the figure, right? Look at this. This end A, it is suspended through this wire and connected to the negative terminal of the battery. This end B is suspended and this wire is just wrapped around the stand so as to keep the wire there stationary, right? And it is connected to the positive terminal of the battery through a key. This much you know now. Now think about this. Where is the direction of the magnetic field? Here, north to south, south to north. Because this place is not inside the magnet. This place is not inside the magnet, right? The direction of magnetic field inside the magnet is south to north, but outside is north to south. So the direction of magnetic field is like this, right? So what we realized, what was experimentally seen was, when this rod AB is placed between the horseshoe magnet such that the south pole is on the top and north pole is at the bottom, and we keep the key, like we place the key inside we insert the key and the circuit is completed. That means current is flowing in the circuit. So what happens is that this this rod AB is displaced towards the left side. What does that mean? It moves quickly towards the left side. That means it experiences a force towards the left side. Okay. Because an aluminium rod in itself doesn't have any magnetic properties, right? Why would a magnet exert any force on a normal piece of material, right? If there is a plastic kept near a magnet, it would not exert any force on it. It would, yes, the magnet will pull a magnetic material towards it, but for this we have taken a material which is not magnetic in its nature, but when current flows through it, obviously we know that the current produces a magnetic field. That is what we have learned throughout this chapter, right? We learned that current flowing in a wire gives rise to a magnetic field, like we did in case of a straight wire, in case of a circular loop. We know that. So what we want to study here is how can we change the direction of the force on this wire AB? Because now we know this much, that when current flows through this wire AB, that means there is a magnetic field produced in AB. It experiences a force towards the left. Now, why did it experience a force towards the left? Can in any case it experience a force towards the right? That all we are going to see. So this much we are clear that a force is experienced by this wire AB or the rod AB. So let's read in your PPT quickly. Okay. So it says that the French scientist Mri Ampere, can you realize something from his name? This Ampere, he is actually the one that the unit of current ampere is named after. Okay. So he suggested that a magnet must exert an equal and opposite force on the current carrying conductor. Okay. So what does this mean? This means that this rod AB, when current flows through it, it gives rise to a magnetic field. Obviously, this magnetic field exerts a force on that horseshoe magnet, right? But the horseshoe magnet is pretty heavy, so it does not show as much of the force. It does not show any change. It cannot get displaced because it's very heavy. But we learned by Newton's third law of motion that every action has an equal and opposite reaction. That means if the rod AB exerts a force on the magnet also exerts a force on the rod, right? But we know that the rod is much lighter than the magnet, so it can easily show a effect due to that force. Like if you are pushing the wall, would you be able to push the wall? You just go stand against the wall and you push it. Would you be able to move it? No, right? And you can feel some kind of force on your hand too when you're pushing it. Why is that? Because the wall is pushing you with the same force back. Okay, so similarly, the rod exerts a force on the magnet, but because the magnet is much heavier, it does not get displaced or anything, and the magnet exerts an equal and opposite force on the rod, and because the rod is suspended by its two ends, it can easily move and it is lighter, so it gets displaced. Okay, great. Let's move on. So the next thing it says is, let's read here. It says the displacement of the rod in the activity suggests that a force is exerted on the current carrying aluminium rod when it is placed in a magnetic field. This magnetic field is due to the horseshoe magnet, right? Because it was placed between the north and south pole of the horseshoe magnet. Okay. So we know this much, that it experiences a force. Okay. Now, what are the factors that affect the direction of the force on the conductor? So it says that the direction of force is reversed when the direction of current through the conductor is reversed. What does that mean? If we connect this rod AB in the form like A is connected to the negative terminal, B is connected to the positive terminal. So if the displacement is towards the left, what happens when we make this like this? If we make this, if we change the polarity of the battery, changing the polarity of the battery just means flipping the battery. That means if the negative was here and positive was here, you just flip it. Okay. So what happens in that case? The rod gets displaced towards the opposite direction, that is the right. So that was the second thing that is noticed. The first thing that is noticed is the rod experiences a force. The second thing that was noticed is when we reverse the direction of current by flipping the battery, by changing the polarity of the battery, the force direction is also reversed. So again, I'm coming here to your PPT. This shows that the direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. Okay, so we notice that by changing polarity of battery, what does that mean? What does changing polarity of battery mean? That changing orientation. You can say it in this way. Changing orientation means that if it was negative positive, you make it positive negative. You just change the orientation, right? That is what we call by changing the polarity. Okay, that is the technical term we use for it. By changing polarity of the battery, which means changing orientation, the direction of force is reversed. Also, by changing the way horseshoe magnet is kept, direction of force is reversed. What does that mean? If we keep the battery like this only, we don't, again same thing, when we want to see the effect or the change due to any two variables, we always keep one variable constant and we change the other variable and we see what difference there it makes. Then we keep the second variable constant and we change the first variable. We can't change both of them at the same time, otherwise everything will get mixed up. Then the changes would be because of both the variables, right? So you won't be able to study the changes properly because of one variable. So when you change the polarity of the battery, what do? You keep the horseshoe magnet in the same way, that is south above and north below. Second time, you keep the polarity of the battery same. You keep the negative here and the positive here as it is in the figure, and you flip the orientation. That means you make it like this. You make the magnet in a way that north is above and south is below. Okay. So in both the cases, by changing the direction of current and by changing the orientation of the magnet, we see that the force is reversed. That means it was going in left in one case and the rod goes to the right after it is reversed. So that is what this means, that the direction of current and the direction of magnetic field is the two factors that the direction of force depends on. Okay, great. Now keeping all this in mind, let's move on and see. Now, factors that affect the direction of force in the conductor, we see that again, this is also experimentally observed that the displacement in the rod is largest when the direction of current is at right angles to the direction of the magnetic field. Okay, what does that mean? That if the magnetic field is in this direction, the current is in this direction, so that there is a 90-degree angle between them. Now in this case also you can see that the magnetic field is like this. It is in a straight line, right? Look at this. This is south, this is north. So the magnetic field is from outside, so it's from north to south, right? And the current is, it looks like it's a little, tilted to us, but it is actually like this. The rod is kept exactly going from the middle of the magnet, so that there is a 90-degree angle between the current and the magnetic field. Okay, this is also a very important point that we are going to use in the next few slides, in the next few applications also. Okay, now let's move on. This is a very, very interesting rule. So first you had studied the right hand thumb rule. Then you had studied the corkscrew rule, which was basically the same as right hand thumb rule. Now this is a new rule, which is the Fleming's left hand rule. I find this very interesting, honestly, and you have a lot of fun trying to, figure out the directions of the force and the current and the magnetic field using this rule. So let's see this without any further delay. Okay, so this says that if you stretch your thumb, your forefinger and your middle finger of your left hand in the way that they are mutually perpendicular. So mutually perpendicular means that each of the three, that means your thumb, your forefinger and your middle finger, your thumb, index and middle, should all be at right angles to each other. So if I want to arrange my thumb and my middle finger at right angles, how would that be? Like this, right? A perfect right angle between them. Now, if I want to arrange my middle finger and my index finger in right angles, how would that be? If I open it like this, are these two at right angles? No. I can't make a right angle like this. My fingers will break. So I choose a different direction. What do? I try to take my middle finger here. So, can you see now? The angle between my middle finger and my index finger is 90 degree. My angle between my thumb and my index finger is 90 degree. And the angle between my middle finger and my thumb is also 90 degree. Oh, that was pretty much of an exercise. So, that is how you hold your fingers in case of Fleming's left hand rule. Okay, looks like this. You should be able to see it from all directions now. Okay, this is how we hold our finger for Fleming's left hand rule. Now, we are going to see what each finger means. Like in case of right hand thumb rule, we had said that if the thumb points in the direction of the current, the curling of the fingers is giving the direction of magnetic field, right? So now we'll see what each finger means in case of Fleming's left hand rule. Great. So it says that they're mutually perpendicular. The first finger points in the direction of the magnetic field. First finger means the index or the forefinger. Okay. The second finger, this means your middle finger, in the direction of current, and the thumb will point in the direction of the motion of the force acting on the conductor. So this means if you know the current and you know the magnetic field direction, you can calculate which direction the force is in. If you know the force and the current, you can calculate magnetic field. And similarly, if you know any two of these three, if you know the direction of any two of these three, you can find out the direction of the third. Now, keeping this in mind, go back to that activity 13.7 that we just did, in which we said the rod will be displaced towards the left. Now, keep your fingers in the direction, keep your index finger in the direction of the magnetic field, which was in case of a horseshoe magnet, north to south, so it was pointing upwards. Great. Your middle finger should point in the direction of current. I remember the rod was somewhat like this, so the current would be somewhat like this, right? So your thumb points in the direction of the force. My thumb is pointing towards the left, and that is exactly what we said. We had said that in the first case, the thumb or the force would be experienced in the left direction. So now it is going to make sense to you. Okay. So remember this rule. We are going to use it in a lot of things going forth from here. Okay. So thumb, force, index finger, magnetic field, and middle finger is the current. Okay. Keep this in mind. Great. Let's move on now. So the applications of this Fleming's left hand rule. So these are some of the applications of the setup and the phenomenon that we just saw, which uses a magnet like we used a horseshoe magnet. Any kind of magnet can be used. So a magnet and a current carrying conductor. This kind of a setup is used as an application in many devices like this. This is an electric motor. This is an electric generator, and everyone knows that this is a speaker. So many other devices like these devices use this setup of using a magnet and a current carrying conductor, and use the Fleming's left hand rule application to produce some kind of force to run something or do some purpose or a job. So we are going to study in detail about the electric motor and the generator in a bit. Okay, let's move on. Now, magnetism in medicine. So this is also a very important thing that you need to know. You already learned at the beginning. I told you that an MRI, which was a magnetic resonance imaging, was a very important medical procedure that is conducted for, getting scans of different parts of the body so that the doctors can see where any problem is in your body. So the two main organs which use these magnetic fields, or magnetic fields are significant in our body also, are the heart and the brain. So these are the two main organs in the human body where the magnetic field produced is significant, and that magnetic field can be, caught by some devices, and if there are any problems in our heart related to our brain, they can be easily scanned and brought on paper using these magnetic fields. Okay. So now that we just talked about the MRI machine, I'll just show you a short video which will show you how a person is, scanned using the MRI machine and how the scan actually looks. It is super interesting. So let's see that. So here you can see that the doctor is sending the patient inside the MRI machine. This huge circular thing is the whole machine. And you saw that he fitted something near his head, right? That is basically the device that captures the magnetic field, which is the magnetic field lines or the magnetic field that is radiated by the brain. We just saw that the brain and the heart produce magnetic fields, significant magnetic fields. Now this is the scan. This is the actual scan or the MRI scan of the brain. So you can see there are some changes that are coming when you observe the brain. So you and I can't understand it because we're not doctors, but from a physics point of view, you can understand that the magnetic rays or the magnetic field lines that were emitted by our brain were captured by that MRI machine, and this scan of our brain is produced, which the doctor can then study and tell us, like, this is what the problem seems to be. You know, if someone has any tumor in their brain, that is how this is detected. That is the process that goes on behind detecting the problems that can be related to the heart and the brain. Oh, sorry, the heart and the brain. Okay, great. Let's move on. Okay, so this is again just the explanation of MRI while telling you the magnetism in medicine and how magnetism is used in medicine. Okay, so here it says the magnetic field inside the body. We just learned that significant magnetic field is produced in our hearts and brains, right? What do we mean by significant? By significant we mean that magnetic field that can actually be, captured to study the images of the heart and the brain. Maybe other parts of our body also, produces some magnetic field, but it's not as significant that it can be studied. Okay. So here it says this forms the basis of obtaining the images of different body parts. This is done using the magnetic resonance imaging or the MRI technique. So analysis of these helps in the medical diagnosis, so that the doctor can tell you, like, okay, this seems to be the problem with your heart, this seems to be the problem with your brain, and so on. Okay. Now, we have example 13.2, which asks us, an electron enters a magnetic field at right angles to it. So even if it doesn't matter in this question, it should come to your brain that we had said that when the current and the magnetic field are at 90 degrees to each other, we experience the most force. Okay, this is something that you should start thinking about now. Okay, so it says that an electron enters a magnetic field at right angles to it, as shown in the figure. The direction of force acting on the electron will be what? Okay, so this is our direction of the magnetic field. Great. And this is the direction of the electron, that the electron is going like this, downwards, and the magnetic field is towards east, right? Now, we know using Fleming's left hand rule, my index should point towards the magnetic field, my middle finger should point towards the current, then my thumb will give me the direction of the force. Okay, so let me point my index finger towards the magnetic field. Okay, my middle finger should point towards the current. Is my middle finger pointing towards the current? Right now my middle finger is towards the direction of the flow of the electron. So, is the direction of the current in the same direction of the flow of the electron? No. See how beautifully we use the smallest of concepts that we have learned in further studies of our physics, right? It is very interesting if you actually think about it. We learned this so way back when we were studying current electricity, that like we should go in the opposite direction of negativity, and electrons are negatively charged, current also goes in the opposite direction. So we had learned that because electrons flow from the negative to the positive terminal in the battery, current flows from the positive to negative terminal, right? That means current flows in the direction opposite to the direction of the electrons. Now think about it. My index finger should point towards the magnetic field. My middle finger should point towards the current. So where should my current be? Is my current downwards? No, my current is exactly opposite to the flow of the electron. That means upwards. So I point my middle finger upwards without changing the direction of this, right? You have to always, once you settle on, okay, like this is supposed to be the arrangements, then check with the figure again. Is my middle finger pointing in the direction of magnetic field? Yes, it is. Is my index finger pointing in the direction of magnetic field? Yes, it is. Is my middle finger pointing in the direction of current? Yes, opposite to the flow of electrons. So, where is my thumb pointing? It is pointing into the page, right? If this is the page, if you draw this on a page, if you draw magnetic field towards the east and electron towards south, then you arrange your fingers in a way that you arrange it according to the page. Then you will see that your force is actually going into the page. Okay, or you do it like this. Like you just keep a page in front of you and draw this figure, you will understand. So you will see that your thumb points downwards or into that page where you have drawn it. Okay. Okay. So when you do this, when you arrange your fingers according to Fleming's left hand rule, and you do it so that you arrange your fingers when you draw it on the page, you arrange your fingers according to that, you will see that your thumb is pointing into the plane of the paper. Okay, so how do we write the answer for this? We write the answer by saying that we write using Fleming's left hand rule. We find out that the force is, you write the whole word, force is into the plane of the paper. And if you want to write an explanation for it, you write this also, that current flows opposite to electron flow. Okay, great. Let's move on. Now, the next question says, which of the following property of a proton can change while it moves freely in a magnetic field? There may be more than one correct answer. Okay, so we take this point by point. We think if each and every one of these properties of a proton can or cannot change in a magnetic field. We take mass. Do you think mass of a proton can change due to the magnetic field? No, because mass is always a constant quantity. No matter if any force is exerted on a particular object, be it a proton or a human being or a car, whatever it is, the mass remains the same. The mass doesn't change according to, even if it's going into a magnetic field, coming out of a magnetic field. So we write that the mass is a constant, so it does not change. Great. Let's move on to speed. Now, the speed of the proton also doesn't change in the magnetic field. Why? To understand this, we're going to go back to the concept of work. So you remember when we had studied work, we had studied what is work. It is force into displacement, right? So we had studied that it is when the work done, when the force and the displacement are at 90 degrees, the work done is 0. So think about it. We had studied the Fleming's left hand rule, right? We know that if our force is denoted by the thumb and this is the direction of the current, that means the proton is the positively charged particle. So it always goes in the direction of the current. Proton is in the same direction as the current and electron is the opposite direction. So if this is my force, then this is my current or the proton moving, right? So these are at 90 degree. That is why the work done is 0. And if the work done is 0, the speed does not change. So we write that as force and direction of movement are at 90 degrees, work is 0, therefore speed does not change. Okay, to understand this, you have to go back and study your concepts that you studied in ninth of work. Okay, great. Now about velocity. You know that the velocity depends basically velocity is magnitude and direction. What is magnitude? Magnitude is basically speed. So the magnitude component of velocity is speed. So we have seen that the magnitude component is constant, speed is constant. Now direction. The force on the proton because of the magnetic field can change its direction. So that means even though speed is constant, the direction can change. As direction can change and velocity is dependent on direction, therefore velocity can change. Okay, so velocity is the first thing that we have seen that can actually change. Now momentum. What is the formula for momentum? We used to denote momentum by P, and P is equal to m into v, where m is the mass and v is the velocity. So now can mass change? No, it can't change. So momentum can only change if the other quantity can also change due to the magnetic field. Can velocity change? Yes, we just learned in the previous point that velocity can actually change while a proton is moving in a magnetic field. Therefore, we say as momentum, I am representing momentum by P, you will write whole, depends on mass and velocity, and velocity does change in a magnetic field. Therefore, momentum also changes. So thus you can write one concluding line that the properties of a proton that can change are velocity and momentum. Okay, great. Let's move on. Okay, so let's move on to the next question. So the next question says, in the activity 13.7, how do we think the displacement of the rod AB will be affected if, and we are given these three cases. Okay, so we go back to what we had studied, that if we increase the current in the circuit, then the magnetic force also increases, so the displacement will also increase, right? So we know that the force increases, so displacement increases. Okay, now a stronger horseshoe magnet is used, again the force increases, so displacement also increases. And this was what was not studied. We didn't study this point at that time, but this is also something that you have to keep in mind, that length of wire, when it increases, again the displacement increases. Okay, so these are the three things. So in the answer we write the displacement of rod AB depends upon three factors. 1. Current in rod. 2. Magnet strength. And 3. Length. Okay, so now we know, combining these three sentences, you can write a concluding sentence that when each of these is increased, it causes an increase in the displacement. Okay, that means if current is increased, the displacement of rod increases. If a stronger horseshoe magnet is used, the displacement of rod increases, and if the length of the rod is increased, the displacement of the rod increases. Okay, great. Now, this question says that a positively charged particle or an alpha particle, this is a new concept for you. This is one type of positively charged particle. Like proton is positively charged, there is another type of particle called alpha particle, which is positively charged. So, it is projected towards west and is deflected towards north by a magnetic field. So the direction of magnetic field is, so to calculate the direction of magnetic field, we are going to use Fleming's left hand rule, using left hand rule. Okay, now we're saying that a positively charged particle projected towards the west. That means this alpha particle is moving towards the west. Okay, that means its direction is this. Now, which direction would the current flow in? If this was an electron, the current would flow in the opposite direction to it. But we saw that the current flows in the same direction as the positively charged particles. Thus, if the alpha particle is flowing from the east to west, the current will also flow from the east to west. So the current direction would be the same. So this is flowing towards the west. Now it is saying that it is deflected towards north. Deflected towards north means that the force exerted on it, it's towards the north, right? Like if I push you in one direction, if I push you forward, you will not fall backwards, right? You will be pushed in the direction that I exert force on you on. So it's saying that the deflection is towards the north. So if I draw this is north, south, west and east, right? These are the four directions. So we were told that the alpha particle is projected towards the west. Okay, great. Then the deflection is towards north, which means the deflection is like this. Sorry, not north. This is the deflection. Now, deflection, which means the force. This we have deduced that obviously if the deflection is in that way, the force is also in that way. Great. Using Fleming's left hand rule, this is supposed to point in the direction of the magnetic field, which we don't know the direction of. So what do? We point these two fingers in the direction of the variables we know about. So my middle finger is supposed to go in the direction of the current, right? So my middle finger goes like this, and my deflection or the force is the thumb. So it is supposed to be like this, I think, right? Yeah, current like this and the force like this. So according to this, my magnetic field should be coming upwards from the paper. That means outwards from the paper. Okay, so you will write using Fleming's left hand rule. We can see that the magnetic field is coming out of the paper. So again, you can only understand if you do it yourself. Again, once more I am explaining. Middle finger, direction of current. Okay, so it's supposed to be like this, going towards west, right? You do it according to your paper. If you draw it on your paper, then place your hand according to that paper. Place it exactly in the direction of the current you have drawn. So I have drawn it on the screen, so I am doing it according to the screen. So my plane is the screen. Your plane will be the paper. So you would place your fingers according to that. Okay. So this is my current. My force is upwards, right? So I can see that my index finger, which is the magnetic field, is pointing towards me, which means it is coming out of the screen for me, coming out of the computer screen for me. So for you, it will be coming out of the paper screen. So it will be going upward. So my correct answer is D. Okay, students. So in this lecture, we studied about the force on a conductor. We studied the Fleming's left hand rule, and we studied how we see which direction the force, current and the magnetic field are in. Now in the next class, we are going to start with electric motor, and that is going to be an application of the Fleming's left hand rule, including all the things that we have studied till now, the right hand thumb rule and everything about the magnetic field. So make sure you are prepared with all of those topics so that you can understand everything. Okay, I hope you enjoyed this, students. Thank you and take care.